Did you
Okay.
listen for master IOC summer school with this?
It wasn't the plan, but it happened.
You have that.
Okay, so that's enough from that, and now turn it over to the Van just to start off telling us where it's from.
Yeah, that's true. If you could leave these on, because I will use the blackboard every now and then, perhaps.
Yeah.
I think
Yeah.
I'm in charge. Okay. Okay. I'll do this first then. Good morning. I'm Wubbe-Jan Veldhuis from the Netherlands, and I come from the University of Twente, which is the electrical engineering department is shown here. This is where I did my PhD on learning feed-forward control. That's what I will be talking about this morning. Just to give you a little bit of an overview of what University of Twente does. We have all sorts of engineering faculties. This is one of the electrical engineering, and you see that it's beautifully situated in a park. I studied at the control laboratory, and what we try to do at a control laboratory is a couple of different disciplines, the modeling and simulation. We like to do intelligent control. I'm not sure what intelligent means anymore after Mark's presentation. We like to be busy with the design of mechatronic systems, so we have a very strong focus on mechatronic systems. Also robotics, tools for mechatronics, and embedded control systems design. But really the main points are the control systems, the mechatronic systems, and the intelligent control. One of the topics we're heavily focused on is the so-called smart disk, which consists of a stack of piezo actuators and sensors. Actually, they're the stacks of piezos. One is used as an actuator, the other one is used as a sensor. And we use this to damp vibrations in frames, for example, in wafer stages. And over here you see the wafer stacks, which damp the vibrations.
What did you call it? The so-called what?
Smart disks. Theo likes to call them smart disks. So our Van nicely mentioned all the inventions coming from his state, so I'll focus on the inventions of the Dutch a little bit. Our control laboratory has cooperates with another couple of other laboratories from the mechanical engineering department and of information science, and we like to call that the Drebbel Institute. And actually Drebbel was a Dutch inventor, and he invented a couple of things, such as a breeding machine for chickens, and he developed an automatic thermostat for that. And he was also one of the first to, actually he was the first to build a submarine and actually try it out. So these are some of the Dutch inventions that we have. Because in our opinion, he was one of the first to deal with mechatronics in his time. We named the institute after him. So this is the laboratory I did my PhD at.
In the U.S., we name laboratories after whoever gives a lot of money.
Yeah, yeah. Nobody gives us any money, so that's a problem. none of them would have names. So.
It was invented for when I have a license for special machine or something? Was he?
Yes, as well. Yeah.
He was invented.
Yeah. Yeah, he did. So after I did my PhD here, I worked for a couple of European-funded projects, and after that I went to industries. And let's see. The company I'm working at right now is called IMS. IMS originates from Texas Instruments. And Texas Instruments in the Netherlands makes sensors for automobiles. There's pressure sensors used for brakes and for the air conditioning system. Texas Instruments decided that this was not one of the building the equipment itself, the assembly equipment was no longer core business, and that's why they wanted to get rid of us. Our managers did a management buyout. Another company put in some money, and now we're IMS, and we work for a whole lot of different companies. And we make assembly equipment for all sorts of small stuff. We don't really do the large assemblies, but only the small ones. So you could think of telephone connectors, parts of shaving equipment of Philips. We're also into medical industries. I will show some of the parts we assemble. This isn't the part. This is. So you see some sensors for thermal protection. These are the pressure sensors, and they're virtually in every automobile you buy. There are a couple of these produced by Texas Instruments. We built a tape and reel. We built tape and reel equipment. So we build equipment that runs quite fast. So 2 or 3 products a second, and you have to get rid of these products. You simply glue them on a tape, and you reel the tape, and it goes off to the customer. So we don't do the assembly ourselves. We build the assembly equipment. Connectors, which is an application where you have to insert like 7 pins a second into a connector, and all sorts of other products. And we're a firm of about 50 people, and if we have a lot of projects, we like to hire a lot of people. So the size is very flexible. But what's very funny is that we encounter a lot of the problems Paul addressed yesterday. So hardly anybody in industries knows about control, and if you know about control, you can't do anything with it. So that's so just to give a short.
Your hands are tied before you start.
Yeah, that's true. So I'd like to comment on this only a little bit. So we build these production lines that run at a couple of products a second, and you have to get all sorts of parts out of a tray, and you have to have a flexible pick and place unit to pick products from whatever position you like onto a walking beam where the products are assembled. And we build a servo pick and place equipment for this, which is more or less something like this. So there's a rail here with some guides, and there's a little cart on here. And on the little cart we have another rail like this, so the whole can move back and forth and up and down. And we didn't want the actuators to be on the moving part because we assemble quite light stuff, and moving an actuator would cost too much energy. So we decided to fix the 2 actuators onto the frame and drive this with a belt. So you can do that by adding some wheels over here. And then the belt goes like this. So two actuators drive one belt that drives the mechanism. And by making them rotate in the same direction or in the opposite direction, you can create a horizontal or a vertical motion. And we did all sorts of calculations on this, on what stiffness the belt should be, on what the mass distribution should be, such that we have really nice properties from a control point of view. So we worked on this for a couple of weeks to design it in a proper way, and then you start to buy equipment in which you can actually implement this, and then you end up with some industrial controllers that don't allow you to implement the trajectory you wanted to drive, because it's a synchronized motion, and the hardware has to be able to calculate a 2D trajectory, and they're often very limited. And the next thing is that the control algorithm you designed can also not be implemented into the commercial controller. So you have this controller, you have 6 fake knobs which you can try, and that's it. So you simply tune a little bit. And the bad thing is that also the people who sell this and should be able to support this don't have any clue what it does. So they just come up and they have this little paper, and there are like 5 rules on this that says turn knob 1 until this happens, and then turn it back, turn knob 2, and this is actually 2. That's how it goes. So after all these nice calculations, you can't do anything with it. Gives you a little bit of insight in what you have designed, whether it should work, but doesn't guarantee that it works. So that's quite a big difference between university and the actual application.
One belt can control the 2
Yeah,
different freezers?
the belt is fixed over here,
Oh, okay,
and it
okay.
goes right through. So if you turn this, move this in this direction, you see this one is fixed to the cart. So this one has to move in this direction. If you make it move in this direction, you see that the belt is simply transported here. You remove belt from the upper part of the machine to the lower part, so this piece moves down. You can actually have another, if you put another wheel over here and you add another actuator over here, you can also transport the belt without the whole thing moving. So you can keep the moving part at rest, and the belt just simply is transported through the mechanism. And that gives you one extra degree of freedom by which you can drive a gripper or something over here. So it's a nice equipment. We use this in a lot of assembly lines. For example, to assemble the Philips shaving machines. So that's a little bit of my...
Vibration problems or not?
we do, yes. We do. And also some quite a lot of mechanical problems, because you want it to be very thin. You don't want a very wide equipment. So these motors are pointed up and down, but the wheels are in this direction. So you need to have some coupling, some gearing, and this gearing is a problem when you want to perform a motion of about 50 centimeters by 20 centimeters in a second, back and forth, and these gearings don't do well with those forces. So that's a problem. But we manage. So that's more or less what I do now. So you will understand that also in my lecture I will try to present it from a practical point of view. Does it work? Over here it works, but we do seem to have some scaling problem though. And Kevin left. Does anybody have an idea how can downsize this? Yeah. No. Yeah, but you will miss half of the slides. Now it's okay. Now I see everything. No, wait a minute, where is it? Okay, here it is. Okay, simply start it up again, and it works. So what I would like to present today is a learning feed-forward control algorithm. I would like to discuss the theory, the design, and show you some applications. And perhaps if I have some time left, I will address some other applications that I did during my PhD, which are not directly related to learning feed-forward control, but also involve learning control and maybe give you a little bit of a different viewpoint on things. I did this together with my supervisor, Theo de Vries, so who is also Mark's supervisor. Okay, first of all, I would like to give the scope of the research, show what goals we have. I will shortly address this, that the learning feed-forward controller is quite related to the iterative learning controller. The implementation of the learning feed-forward controller that most resembles the iterative learning controller is a time-indexed learning feed-forward controller. I will go into the design issues, address some the stability. We did some stability analysis. Afterwards, I will give you the path indexed learning feed forward control, which is actually the one we are interested in, and I will address some design issues. Shortly address the stability, which is still quite an open issue, and then I will present some applications. So the control laboratory at the University of Twente, at least the one at the electrical engineering department, is quite practically oriented. So we would like efficient control of mechatronic systems. So we heavily cooperate with industries. So what these people want is a high accuracy. They want to get this in a limited time, and they also want to get this at limited cost. A little bit more about the accuracy. One of the applications, I have to interrupt. One of the applications I've been working on is a linear motor, and I will address this linear motor quite often. So, what do we want with the high accuracy? In this linear motor, if you use a standard controller, it's only the motor can be only used for a limited amount of applications. And I would really like to do this high-end applications with the same motor without actually improving the mechanism itself, because it would become much more expensive. So what we would like to do is keep the same motor, keep a cheap motor, and make it perform better than the standard motor. What industry also wants is to keep the same performance, only use cheaper parts. So you downgrade your equipment, but then again you upgrade the performance using control. We would like to do this in a limited time, so without a whole lot of modeling your process. So we'd like to use some sort of practical identification. We'd like to use this in the design and in the analysis of the controller. So we would like to be able to incorporate identification that we did on the process, and we would also like the controller is able to incorporate knowledge of the engineer. So we don't want some sort of black box mechanism that you often see in neural networks. So they take one large neural network, hook up a process, and then something happens and nobody knows what happens. In the end it either goes right or wrong, but you didn't have any possibility to include your own knowledge. So the thing had to work it out all by himself. So we don't want that. So we want to do this at a limited cost, which often means limited time and limited effort. If we achieve this, the equipment will be more competitive compared to other equipment. So, I would like to address the class of systems that I'm considering. And, you will see that it's quite a limited class. It's not such a wide class as the iterative learning controller is able to cope with. But in this limited class of systems, there are numerous applications for which this works. So one of the professors at Twente tells that the world is a fourth-order system, which I didn't draw here, so which might be a little bit confusing. But most systems in some sort in the lower frequency range behave as a fourth-order system on which some disturbances act. And I would even like to downgrade this class even further into the rigid body mode of this fourth-order system. So we're practically, and I will show this later on, why we have to consider this class and why it's only a very limited class. But we simply consider the rigid body mode on which some sort of disturbance acts, and this disturbance might be non-linear and might depend on the states of the process, etc. But that's more or less the class of systems we would like to consider.
What did it say, justify fourth order?
Because
rigid body mode and a vibration? Or
yeah,
what?
yeah, it's where you have it. He said almost anything can be written like this in the part of the dynamics where you can actually influence this and control this. Everything that's above this is uncertain. So He actually only considers this part of the mechanics, and he also gets quite a performance out of this. So from a practical point of view, it's right. From a theoretical point of view, of course not. But if you consider all the applications, they more or less behave like this. So we end up having only a very limited class, but I will show you that in this class there are some quite nice applications which we can do. So it doesn't work for everything. In this, on the process we consider random disturbances, so random noise acts on the system, and there are also some reproducible disturbances. And these reproducible disturbances might either depend on the state of the plant, or on time. There may also be influences coming from outside acting on the process that depend on time. The reproducible disturbances you may consider nonlinear friction, which doesn't change too much in time. In the linear motor you've just seen, there are some heavy cogging effects, which can also be written like this. And I will also show why the linear motor is quite a nice application for this, because it doesn't have the flexibility like the robot Michael said. So Michael, after achieving quite a nice performance, ended up having a quite bad performance at a point where he actually wanted the accuracy. With a linear motor, we don't have these problems because it's stiff. So for this class of systems, which is generally known, we can quite accurately control this using a feedback controller and a feed-forward controller. And what we would like to do is get robustness through the feedback controller and accuracy through the feed-forward controller. But it's all quite basic. So a little bit back to the industry point of view. Feedback control is used also throughout industry, even if people don't actually know what they're doing. They often only tune the PID controller, but they get quite a good performance out of this. At least it's satisfying. But the feed-forward part is not fully exploited. So there often is one term in there which allows you to do a little bit feed-forward, but it's very limited. So therefore, we would like to focus on the feed-forward part, like iterative learning control does. And we would like to do this in the framework we've just shown you, so with a feedback controller in it, because you can increase performance and also keep the robustness. You get a robustness through the feedback controller, and you get a performance through the feed-forward controller. So this was also quite an important issue, because many learning controllers throw away the feedback part. So you throw away the control you have, and you have to start all over again. So you don't know if you're actually going to end up with the same performance you had before. So it might actually be that the performance first decreases and then increases. But we don't want this. So we would like to keep the performance we have and only increase this performance. So we would also like a very predictable learning behavior. Also in this learning feed-forward controller, so we focus on the feed-forward part, we would like the the knowledge of the engineer in there, identification. We would like to incorporate results coming from identification, and of course it has to be able to cope with nonlinear disturbances. When we studied the learning feed-forward controller, we did this from a learning point of view, so coming from the neural network community. And we didn't make many advances until we found the link with the iterative learning control. So we were able to improve the performance, but some phenomena came up that we couldn't explain. So from a neural network point of view, it's often quite difficult to explain what precisely is going on. And then somebody came up with a link with iterative learning control, and then some pieces fell into place, and we could understand the learning behavior a lot better. So that's why I would like to link learning feed-forward control with iterative learning control. As you've already known from quite a lot of lectures. Iterative learning control solves the time-dependent disturbances. And at Twente we do not aim for zero tracking error. So we try to compensate for the less known dynamics, of which you know a little bit about the phase and a little bit about the magnitude, but there's some uncertainty in there, and try to learn a little bit of that. So we often incorporate a Q filter which doesn't result in a zero tracking error, but will give you quite good robustness. As also was addressed, there's a difference between the iterative learning controller and the repetitive controller. And we tend to do more of the repetitive kind of control, because it also the points that were pointed out yesterday, it takes a lot of time to get the system back into a stable state and into the initial state and start all over again. So we like to just keep on experimenting. So we apply the repetitive controller. As was pointed out, the learning filter gives you the performance. Quite a lot of people address the design of the learning filter, and the Q filter has to filter out the unstable parts of the feed-forward signal and give you robustness. And we always incorporate the feedback controller, because we would like to add this onto a existing controller. So our clients already have a control system and simply want to add this part to it to increase the performance. So it's not acceptable to throw away the feedback controller and start all over again. They simply want an add-on. Also because you, as Michael and Paul addressed it, it's difficult to get into this part of the controller, because this is what is the difference between one manufacturer and the other. So they're not likely to give you all the information. So they often say, okay, here you have it, you can insert your signal here, that's a measurement signal, but that's all you know. So we don't do anything with that, we just keep it intact. This is pretty much what I already said. So now we'd like to give the relation between the learning feed-forward controller and the iterative learning controller. Coming from a neural network point of view, we didn't focus on the repetitive motions at first. So we wanted to learn a whole lot of motions, and so we did have a different viewpoint. So iterative learning control only applies to these repetitive operations, and is able to deal with disturbances that are also repetitive or and that depend on time. What our customers would like, or client, is to be able to accurately perform a whole range of motions. So they often don't have this repetitive operation. So in assembly equipment you do, because you simply perform the same task all over again. And in that case you should apply iterative learning control. But some of the applications we have involve random motions. And we would like to be able to use the knowledge of the iterative learning controller, of the learning mechanism, and apply this to random motions.
Really mean random?
Excuse me?
You want to simulate Brownian motion?
No.
Arbitrary.
So yeah, arbitrary motion. No, not like no. So we take some of the knowledge we gained from iterative learning control, and we would like to extend this. And as I said before, it doesn't work for the large class of systems. It only works for the more or less for the rigid body mode on which some disturbances act. So we would like to keep the stable feedback controller and some sort of learning feed-forward part. But as you have more or less have the cycle time as the input in the iterative learning controller, we now need some different signals, input signals, because we want to track these arbitrary motions. And with that comes that we would also like another storage mechanism. In iterative learning control, you simply store all your data in a table, which is fine. But once you go up to higher dimensions, these tables become huge, and they have some properties that we would not like. So we need some other kind of storage mechanism to hold the feed-forward signal. And as it turns out, a large part of the behavior of the learning feed-forward controller comes from this storage mechanism. So it depends on which storage mechanism you use, what kind of behavior you get. So this is more or less what we came up with, or what we started with before we knew the connection with the iterative learning controller. So we have the feedback controller again, but now we have some sort of neural network over here, which is nothing more than a function approximator, nothing great going on there. And the input of the neural network consists of the reference trajectory and derivatives thereof. So the feedback controller again compensates for the random disturbances, and the feed-forward part, the neural network, is to cancel the reproducible disturbances. The neural network needs some sort of learning signal, which indicates how the feed-forward signal should be updated, which is actually the L in iterative learning control. And here we simply take the feedback controller as a learning filter.
Why
So
doesn't it take the error signal directly?
you can, yeah, you can. So I didn't focus too much on the on which learning signal to use. You can also take the error, feed it through some sort of L, and then feed it to the neural network. That will give you a different performance. But in this research, we're more into the behavior of this. So on when does it become stable? When does it become unstable? And that's not directly influenced by the L. So that simply shifts the problem. But we would first like to explore the learning behavior. So you can increase the performance by not using the output of the feedback controller, but use some L to learn. And this is based on literature where they used a multi-layer perceptor network over here, and I will get into that a little bit later. Yeah, let's see where I am. I have to point out that we wanted to learn these random motions or arbitrary motions. So we looked into a couple of learning schemes. You can also take the feedback part and make that learning. But the learning behavior is quite difficult to predict. That makes it difficult. That's why we chose this part. So we imagined that the performance would only increase. However, it didn't. You've seen plenty of pictures of this, how the tracking error decreases, the output of the feedback controller becomes less, and as you proceed more, the feedback control takes over most part of the control and cancels cancels the dynamics. And this was more for the graduate students. Many of the people who came up to us thought that we would only learn the output of the feedback controller and that's it, but we actually learn more, so it accumulates. But this is general knowledge after all we have seen. There's often a lot of confusion about the neural networks. Quite large claims are being made of them being able to learn, and that they would be able to produce some intelligence, but from our point of view, all that is not true. So in the way we use them, they are simply universal function approximators. So they learn on the basis of data. They do some interpolation, they do some extrapolation, and that's pretty much it. And they have some nice properties and they have some less nice properties. And they're a lot better on the interpolation side than on the extrapolation side. So that's you have to know all this. And in the neural network community, where they also do a lot of control, they often make these heavy claims saying, okay, we have some sort of system here, we know nothing about it, we have a neural network, we feed it some information and everything goes well. So, but from our point of view, that's not the way to handle these. You should look at it from a control point of view and then move forward. So neural networks they're used for universal function approximators. You can recognize patterns with it. You can do all sorts of useful things with them, but they're nothing magical. So please, why didn't we want to use a table? As you've seen in the one of the previous pictures, we had 3 inputs coming into the neural network, which means that you end up having a 3-dimensional table. And if you have to span quite a large area in which you want to move, you end up with having quite a large table, which is not very practical. And it has some properties I will show you later, which we do not want. Well, one of these is a generalizing ability. So a generalizing ability means that if you perform one motion and learn this trajectory, and you perform a motion which is quite similar to this motion, you will also like a good performance. You would also like some of the knowledge that you've already gained. It doesn't need to be perfect, but there should be quite a large improvement. And if you have a table, you do not have any generalizing ability, because you simply learned all these table entries, and if you're a couple of cells away from that, there's no knowledge in there. So we would like this generalizing ability. We need this because we span a multi-dimensional space. So in the one-dimensional space, in case of the iterative learning control, a table is fine, but in our application it's not. There are quite a lot of storage mechanisms. Why did we choose the neural networks? They have this ability to learn, whatever learning means after the discussion. They have a compact storage of data, which means that you can store the data using quite a limited amount of parameters. And they have this generalizing ability, which is quite a nice property. And you do need this.
Can I ask?
Yes, of course.
All the neural networks that you use in the context of this learning feed-forward control, they're static?
Yeah, they're static, yeah. We don't use the internal feedback in the neural networks, no. No, no.
Do you take time delay taps of your inputs into the neural network?
We tried that, but we ended up going back to the picture I just shown, where we use the reference, the derivative thereof, and the second derivative. So it's more or less a 3-input neural net, yes.
But with some derivatives going in.
Yeah, definitely. Yeah. So which is almost the same as when you put this time delay stuff in there. So we didn't use the neural networks with the internal feedback, because that makes it more difficult to predict how the learning behavior will be. So we really wanted this predictable learning behavior, because we actually had to apply it. So you have to know something. You have to know where you're going, because otherwise anything might happen. It might give you a very good result at the end, but in the intermediate phase you might end up having a really large tracking error. So we didn't want that. As I stated, the neural network we started off with was the multi-layer perceptor network. And this multi-layer perceptor network was actually more or less based on the layout of the brain. And that's why they stated that it must have some sort of intelligence in there, or at least it must be able to form intelligence. And the layout of the brain is more or less that you feed in some information into neurons, whatever they may be, and these neurons distribute all the knowledge until to more neurons, and then in layers, and then at the end you get a signal over here. So they claim that it would have some make intelligence possible, but I don't think so. So what do these artificial neurons, which hardly resemble the real neurons, look like? You have a lot of input signals coming in, which might be anything. You actually sum them up, and then you put them through which is known as a sigmoid function. And this is actually all the neuron does it. So it does a very simple operation on the input data.
So why use MLPs? If you want to do fast learning.
I end up with the conclusion that you should absolutely not apply these. So that's no. This is more of a historical perspective, because people used MLPs as for learning, but you end up having all these properties you don't want. So you shouldn't use this. So these are okay for offline processing of all sorts of data, but don't use them in a control algorithm. So how do these neural networks learn? So you feed in the information into the neurons. These neurons pass on the information to the other neurons, but these connections also have a weight. So you multiply the output of this neuron with a weight, and that forms the input of this neuron. And there might be more layers over here, so there might be more weights. And in the end, you get this weighted processed data, which eventually ends up here. And learning goes through back propagation. So you should know where you're going. You should know what your desired output signal is. And then you can calculate the delta. So the difference between the actual output and the outputs that you desired. And you can calculate the derivative of each of these weights with respect to the output. And you simply tune all these weights a little bit such that the output, the difference between the actual output and the desired output decreases. And you can see that even in such a limited amount of neurons, there are quite a lot of weights. So it's very computational expensive. But they do have some nice properties for some applications. So one of these properties was that they have the generalizing ability. So if I track one trajectory, learn until the error has converged, and I then track a motion that is quite similar to this, to the learned motion, we end up having an error that is a little bit larger than the trained motion, but it's still pretty good. So it still gives you quite a large improvement from the original situation.
Looks identical to me.
It's simply drawn using PowerPoint. So no claims here. So when you simply look at this from an input-output point of view, you learn the green dots. You have quite a nice fit through the green dots. You didn't learn the red dots, but it still makes a pretty good approximation of the red dots. So that's a generalizing ability. And this network does have this property, if you learn it correct. It also gives you quite a compact representation. So the input-output mapping is stored in quite a limited amount of weights. And this especially is favorable in the multidimensional case. So if you, for example, would like to control a robot manipulator in which you have several links, then you might have having quite a lot of input signals into this neural network. And the multi-layer perceptron network is able to still approximate high-dimensional mapping using quite a limited amount of weights. So that's very favorable.
Question?
Yes, sorry.
To update the neural net, you need to know some, you need to know some error, however it's doing.
Yeah.
How does that error?
Yeah.
The output of the control.
Yeah.
The pivot control.
Or the output of the L, as you like, if you have L here. So the output of the controller indicates the error we have made, like you do in iterative learning controllers. So the signal after the L more or less gives you the direction in which you should change your input signal in order to improve the performance. So we also, that's why we've drawn it like this. The L indicates the update from the error to the adaptation of the input signal.
Sorry, I missed that.
Okay, so that's more or less this. So you might also write the L and get a better performance than this, but it's.
Do you have any problems about the time delay if we use the multi-layer of the neural network?
You're not heavily into this time delay problems as you are with iterative learning control, because it more or less cancels out in this setting. So it has some filtering properties, like the neural network has some filtering properties, like the Q filter, which takes care of this. Yes?
How do you choose the number of neurons?
That's also in a multi-layer perceptron network. That's also one of the issues. There are some general rules for this, which give you a vague indication, but it's more or less done by trial and error. So you try using a small amount of neurons, then you train, and then you see where it gets stuck, and then you increase the number of neurons, and if the error goes down, you get an improvement. You keep on increasing the number of neurons until the error doesn't go down anymore. So
According to your experience, do you think is there an optimum number of neurons?
there is, but it's you can hardly find it. So this is more or less experimentations. You really have to get hands-on, try all sorts of numbers of neurons, and see where it ends up. So that's one of the things that's not straightforward. So that's the part I don't like. Yes?
Actually, I have a comment here. The C, your feedback controller, if you have an integrator in the C,
You shouldn't.
you should not
No.
have an integrator in your C.
No. If you have an integrator, you should take an L filter. That's true.
That's the point.
Yeah, that's the point. Yes. Otherwise you have two integrators be after each other, and you end up with not a nice performance. Something that might happen in these neural networks, if you take too many neurons, is that you end up having overfitting. And instead of the nice generalizing ability we just shown, you end up having overfitting, which means that you quite well approximate the points you've trained, but once you get a little bit off, you have quite a poor approximation. So you might train really nice on one trajectory, feed it with a trajectory that's quite close, and you end up having a really poor performance. So that's also, if you take too many neurons, this might happen. So you can already feel that there are quite a lot of tuning parameters which are quite unpredictable in this setup.
In linear classification, you have like quantities theory or quantities theory. So you weight those, you put your number of parameters in your optimal criteria. So you include that you
You
want to fit to your data.
Yes.
You don't want the overfit. That's why you put those at the number.
Yes,
of
you can.
parameters.
Yeah. You can put a bound on the number of weights. Yeah. Or
Optimal in what sense?
yeah.
It doesn't make sense even for the linear case.
No.
So
That's true. And you might also end up in a local minimum, which is even worse. So because it's a nonlinear mapping, you might not end up having a really nice approximation, but only you might up in a local minimum. So if you draw the error, if these if this is the weight space and this is the error, what the learning algorithm does is that once you're here, it calculates a gradient, and you simply move down to the minimum. However, if you start from here, you end up in this local minimum, and using a gradient method, there's no escape from this one. There are some tricks how to get out of this, but they still guarantee that you end up in the global minimum, and so you might end up having quite a poor approximation. And we've seen this on experiments where we had a two-link robot, and we fed it a trajectory, and the error didn't converge anymore. So we thought, okay, we're in a minimum now. We fed it a completely different trajectory, and also the error converged. And then we went back to the first one, and after learning, we actually obtained a smaller error than in the previous convergence. So we ended up in this local minimum, and after feeding it some other trajectory, we somehow went over this and went to what is most likely to be another local minimum, but just a better one. So this is not a theoretical problem, but you actually encounter this when you do experiments. So they're all kinds of properties you don't want. So it gives a very compact representation. You might end up having a good generalizing ability, but it doesn't have a very good predictable learning behavior. You might end up in this local minimum. You might have this overfitting. So, yes?
Just wondering, when you say global minimum, have you then, can that be an overfitting because you have modeled some noise? And
Yes, yeah, that can. It depends on the data you feed it. That's true.
So
You might end up fitting the noise, yeah, if you take.
So you're more sure if you take the first local minimum that is robust compared to the global.
No, it's true.
So there's no guarantee to find it at all.
No. No, there isn't. No, you have to feed it. In the experiments we did, we had to feed it all different kinds of trajectories. And once we got stuck, we fed it another trajectory. It improved, and then we went back and forth, back and forth. And after a couple of iterations, we got acceptable performance. But it already shows that it's heavily depends on the inside of the engineer, what performance you will have. And this is not a property we would like. So we looked into other types of neural networks. There are many more, and we picked a B-spline network, which is generally a table with some interpolation. So you stay quite close to the iterative learning control memory. And actually, this B-spline network does give you quite nice properties. We also did, yes. But you can also shift these basis functions also shift, so that it's they're not fixed. So the width of the basis function changes, and their location also changes. So if you feed it like if you uniformly distribute it and you feed it a lot of experiments over here, these basis functions might shift, and then you end up having almost nothing over here. So when you get back, you have a poor approximation. So the shifting of the basis functions was why we didn't proceed with this one. This is more or less the radial basis function. It looks a little bit different, but with the position fixed and the width fixed. So our approach was a B-spline network. In a B-spline network, we would like to approximate a signal using so-called B-splines, which are basis functions that consist of piecewise polynomial functions. I hope you can see it, but here's a triangular one, which is known as a second-order B-spline, and here's more consists of third-order, second-order splines. And it's third order, yeah. Who knows? That's a matter of definition. These be on the input universe we would like the mapping from. For example, in this example, we would like a mapping from R, from the reference position, to some kind of output signal. We distribute these basis functions, and we distribute them in such way that their sum always equal, their height always sums up to 1. So in the triangular case, a B-spline starts at the top of the of another B-spline. A little bit of a mistake over there. So they always sum up to 1, and the output, of the B-spline network is a weighted sum of these B-splines. So if you would like to approximate this signal, these are the weights that correspond to the approximation. Well, I will show this later. So actually, you multiply this by a weight, so you get a large triangle. You also multiply this with a weight, you get a large triangle. You add these up, and you get this piece. Which can also be shown like this. So you more or less have these basis functions over here. These didn't turn out to be quite nice triangles, though. You feed it an input. You calculate the height of the B-splines at the input. you multiply the height by a weight, and that gives you the output. So you sum up all of them, and that gives you the output. So in the triangular case, you see that there can only be 2 B-splines active at a time, which is a nice thing. Turns out later. Let's see. In a multi, the B-splines I've shown you here are one-dimensional, so they only extend in this dimension. But you also have these multi-dimensional B-splines, which look like this. So they're triangles on the. Oh, sorry, you can't see her. I'm the only one that can see it, and I know. So you at the middle part you have these triangles, and over here it goes down like this a little bit. So also these are distributed on a 2-dimensional space, and these are also distributed in such way that they always end up to 1. And if you look at it from above, not in the 2-dimensional case, this simply looks like a grid. Of which one B-spline covers 4 of these grids. So there's one of these triangles sticking out here, and over these 4 there's one sticking out here, and their sum always adds up to their height always adds up to 1. These are uniformly distributed B-splines, so at each position in the input space the B-splines have the same size. You can also say, okay, I want some more accuracy here, so I put less white B-splines over there. But in that case, you would have to remember to calculate the height, you would have to remember the whole grid. If you take and know that over here they're a little less wide than over here. If you simply take them the same size everywhere, their height can be calculated quite easily, and which is very favorable for online implementation.
Why do you choose the second order of these? If you use a high order, will it be longer size?
It gives you a little bit smoother output signal, but we started out to enable to be able to predict the learning behavior. It's much easier to take a second order B-spline because you only have 2 that influence the output signal. If you take a third order B-spline network, you have 3 that contribute to the output, so the calculations become more involved. But
When you go to 2 dimensions, it
therefore
scales by 4.
yeah, that's the negative property. I will get that. So it's simply because we were able to do these calculations. If you take higher order B-splines, the calculations become more involved, and we didn't get into that.
Since you mentioned uniform parade, have you tried wavelength? I mean, for a
No, we haven't, no. So, putting it into one equation, the output is the sum over all the heights multiplied by the weight. And learning is done through adaptation of the weights. So the B-splines stay at the same position. So simply what this says is calculate the height of each of these B-splines at a certain input and multiply it with the weight. There shouldn't be an R over here, by the way. As I said, learning is done through the adaptation of the weights. We do not change the position of the B-splines. You could also do this, but then the learning behavior would become less predictable, and we didn't get into that at this stage. So, and these already show to have quite a good performance. You can do this should say online, by the way. You can adapt the weights after presenting one sample. So you calculate one output, you get one error back, and you immediately change the weights. Or you can simply or you can wait until after a run you collected all the data and you update the weights. when you use this learning rule, you do instant adaptation of your feed-forward signal, which can be shown like this. If you're in this B-spline and you calculate the output, the feed-forward signal you feed into the system, and you wait for the output signal, you do the adaptation at the next sample interval, but you're still in the same B-spline, so you end up having some sort of integrator over here. You're at the next sample interval, you're still at the same B-spline. So. The desired properties of the favorable properties of the B-spline network that has a relatively low computational cost, so the height of the B-splines can be calculated quite easily. There are no local minima, and also what we have is this local learning property, which means that when we perform a motion and learn the feed-forward signal, and then wait until and then present a completely different motion, and also learn that it doesn't influence the previous one. In case of the multi-layer perceptor network, all weights in the network contributed to the output. So if you perform one motion, learn until convergence, and then perform a completely different motion, learn until convergence, it would have affected the first motion. So you don't know what performance you end up with when you perform the previous motion again. So that was also one of the less desirable properties. But in this B-spline network, because only 2 of these splines are active at a time, you only adapt these weights, and you don't adapt the weights of the other ones because their height is 0. So you have this learning local property, which is quite favorable. And you end up with having a fast and easy learning mechanism. So it's quite straightforward. It does, however, have a less desirable property. It has the so-called curse of dimensionality. This is exactly why we wanted to get away from the table. If you have a multi-dimensional table, you end up with having a whole lot of entries when you have a multi-dimensional one. In a sense, you also have this drawback in the B-spline network. So if you increase the dimension of the B-spline network, the number of weights grows exponentially. So when you need a very high accuracy and you have a multi-dimensional B-spline network, you end up having a large number of weights, which means that you have large memory requirements. You have to store these weights in some way. You also have large training sets because each of the weights needs to be trained. So if you simply have a lot of weights, you need a lot of training. So if you only have 2 weights, they can be trained easily. But if you end up with having quite a large number of weights, each of these weights needs some training example. So you need to perform quite a lot of motions before this network is completely trained. That's one of the drawbacks. And you also have a poor generalizing ability. So in a 3-dimensional space, if you perform one motion, and a very similar motion might be quite close to this, but it doesn't overlap. So that's a drawback. But we will show some way to get around this drawback. Okay, this is more or less what I already told. So for the poor generalizing ability, I show if you have quite a large number of weights, and you might end up having a poor generalizing ability, which I will try to show here. It's a 2-dimensional B-spline network with rather large B-splines, which are shown over here. And this has quite a good generalizing ability, because if you perform one motion, all these weights have done some sort of training. If you perform this motion, all these weights have done some sort of training. You see that all the weights have been adapted. Also, so if you perform a motion within this space, you would have some sort of feed-forward signal. It will not give you the best tracking error, but it will give you some improvement. So you see that only by performing 2 motions, all of the weights have done some sort of adaptation. However, if you have a really high accuracy, if you have many of these B-splines, by performing this motion, only these weights have been adapted. So,
How come it spreads as far as it does?
the B-spline, over each of these 4 squares, there's this triangle, and you see that when you're in this triangle, in the middle of the weight, you have some input signal over here. So if you're over here, the same B-spline is active, and you have some sort of output signal. It doesn't necessarily lead to a very good performance. We will have some sort of output
As
signal.
long as you're in the 4x4.
Yeah, as long as you're in the 4x4, the weight gets adapted. So you see that the band is much more narrow than in that case. This will give you a higher performance, though. And the other signal, these are the same trajectories as in the other one. So you see that now we have the generalizing ability is not as good as in this one, because over here we didn't do any training there, we didn't do any training over here. So to fully train this input space, you need more trajectories. You end up having a higher accuracy, though. Yes?
So as long as your motions are in that range, you're okay, right?
Yeah, you're okay. You will encounter some sort of improvement.
Is your axis in favor of input space or?
Input space, the input space is this is the position, that's the velocity, for example. If you have the 2-dimension, you have the reference and the reference dot.
You say you'll get some sort of improvement if you're
Yeah.
if you're on the other corner of the set of 4. Is it clear it's improvement or not? Or could you be made?
You might you also might make things a little bit worse, though. Yeah, it might be. Yeah, it has only been touched. Yeah, it should be properly trained. So you should have some motions over here as well. But once you stay close to it, it's okay. Over there, I'm not sure. But I have to correct. Yes. So I first showed you the feed-forward controller using the multi-layer perceptron neural network. That's generally known as feedback error learning. And we put in a B-spline network, and we had to give it another name, so we named it Learning Feed-Forward Controller. And the nice property of this is that we were able to understand the learning behavior, and that was very important to us. And in some sense, you can see that this is related to iterative learning control, because if you perform the same motion over and over again, you only train those weights, like in the iterative learning control case. So the behavior of this network, even though it has these inputs, if you train it with only one motion, should be almost equal to an iterative learning controller. So if that is the case, you do have some understanding of the mechanisms that go on underneath. So in order to understand this better, we not say downgraded, but we went away from the assumption that we would like to perform arbitrary motions and go back to only one motion, but still use the B-spline network in order to understand the learning behavior of the B-spline or the influence of the B-spline network on the learning behavior. So we understood the learning behavior in iterative learning control, and in order to understand this, we first apply it in there and see what the learning behavior becomes. So if you repeatedly only perform one task, generally all disturbances become time dependent, even though they were originally state dependent. And that's one of the things iterative learning control was able to cope with. And so instead of using the reference path as an input, we would like to use the time as an input, as in some way is the case in the iterative learning controller. So we end up having this scheme So we still have a feedback controller. We have the B-spline network, but now the input of the B-spline network is not the reference trajectory, but it's simply the periodic motion time, which resets after each at the end of each motion. So it's not really the equivalent of the iterative learning controller, but more or less of the repetitive controller.
With reset or without reset?
Without reset, we go on because of time considerations. It simply takes too long. What design issues are there? One of the issues is the B-spline distribution that we have in here, and the other one is the learning rate. The company we did this for tried this, and they thought, okay, if we use really narrow B-splines, we might have having a really good performance, because the input-output signal that results from this mapping can fluctuate heavily between these nodes. So you can have a really aggressive input-output mapping. So it's not smooth. So they thought, okay, if we implement this, we're able to learn all the high frequencies, and we end up having a really good performance. So they first started using a low number of B-splines and then kept increasing them, and they thought they would end up having a really good performance. But what they really ended up with was unstable behavior, which is quite logical if you look at it from an iterative learning control point of view. But so intuitively, one would choose a really large amount of B-splines, but actually one shouldn't. And that's because of the amplification in the learning loop. This is exactly what was also presented in the iterative learning controller. So you present some feed-forward signal to the system. Some feedback signal comes back, and the feedback signal only amplifies the feed-forward signal. So you end up having a larger and larger and larger feed-forward signal, and you end up with having a really poor performance, which also can be seen from the formula. So. In a sense, also what you did in the iterative learning controller, if the error that you get back is in some sort in phase with the feed-forward signal that you send, you amplify the feed-forward signal and you end up with having an infinite feed-forward signal, which is the case over here. So if they are in what I call in phase, they amplify, and I will show this later on. So, now I have to find, no, yes. And what one intuitively thinks is that these two are in phase if the phase shift of the closed loop, the transfer function, which was the transfer function between the output of the feed-forward signal to the input, there's a minus in there, but don't care, is larger than 90 degrees. In that case, when you adapt in a certain direction, you actually end up having an adaptation in the other one. So what you try is to adapt it a little bit more in that direction, and you end up having a worse error. And this accumulates, and you end up having nothing. And that typically occurred at these high frequencies. So when these guys at the company tried it with a whole lot of B-splines, they were able to actually learn these high frequencies in which there is a phase shift between what you do and what you get back. And they ended up having a huge amplification, and which was okay for the system because it could do it. But this is the transfer function from the output of the feed-forward controller to the output of the feedback controller. And there is a minus in there, so there should be a phase shift here, but that's not too important. It's from there to there. So, how come when they started off having a small amount of B-splines, that things were not unstable and they ended up having instability? That's because of the filtering properties of the B-spline network. So you can try to approximate really high frequencies using this B-spline distribution, but since the output is linear between the tops of the B-spline network, those frequencies simply cancel out. So the B-spline network is not able to learn this. So what we try to do is find the width of the B-spline distribution, which gives you these filtering properties such that you can learn the low frequencies which you are interested in, but cancels out the high unstable frequencies. So in some sense, the B-spline network that we used is our Q filter. The B-spline network can be viewed as some sort of Q filter and a memory. That's because of the filtering properties of the B-spline network. We did some calculations on this. I will show you roughly what we did, and it showed that these B-splines have they really cut off the frequency. So intuitively, we thought that at a phase shift of minus 90 degrees, that's where things become unstable. And actually, after a whole lot of calculations, we found that the width of the B-splines that is allowed is actually such that is right here on this border. So you end up having not a very good approximation in this area, but you're not really interested in that. But it's actually unable to learn these frequencies. So it's right on there. So we're able to derive a design rule for the width of the B-spline distribution on the basis of identification. So we go up to our experimental setup. We do some experiments. We get a closed loop Bode, the closed loop Bode plot, and from this plot we can tell what width of the B-splines you should use in order to get stable learning behavior. And it's actually right there on the intuitive border. So how did we do this? What we saw, let's see. When these instabilities occurred, we saw that the contents of the B-spline network became triangular, like this. So and there's also some offset in here, but these became really dominant. And what we saw is that this actually only grows. So in a sense, if you have stable learning behavior, if you enter this, it learns.
Go out of the circle somewhere else on the circle, and then you can. So this is optimistic, the 90 degrees. So I'm wondering if you can.
No,
I'm sure you could make an adjustment based on.
We also tune the
more precise.
We also tune the learning rate, so that actually sizes it. So but then you can get this. I guess we can discuss about this later.
But I think you could fine-tune the estimate. I bet that's optimistic.
Okay, we will discuss about it.
This picture is the same as the one in your last
Yeah.
slide. So you said the input is U sub F, output U sub C. Sorry, input is U sub C.
No. results for the learning rate. What we more or less do is I would like to wrap up the time index learning feed-forward controller. So what you do in the design is first you design a feedback controller. Often you already have this because you're designing an add-on on the system. Then you do some sort of identification, obtaining the closed-loop Bode plots, and then you apply the design rules that we already have shown. We did this for the linear motor. As I said before, there's some really nasty effects in here of nonlinear friction and cogging. We try for the identification. We try to get rid of those to perform a really slow motion back and forth, and on top of that, do some sort of insert some sort of identification signal, and which doesn't give you a very well identification in the low frequency part. But that wasn't what we were interested in. We were interested in the part where the 90 degrees phase shift occurs. That's the Bode. Okay, from this Bode plots, the minimum width of the B splines was 0.0192 seconds, and we did some experiments. So these are experimental results, and this is actually this is 20 mu. So yep, this is 20 mu. So that's pretty small. So keeping in mind that we chose this one, I tried a little bit slower, a little bit smaller D, and I end up having convergence at first. So I was really disappointed. So I kept the system running for about 20 minutes and nothing happened. So I thought, okay, I have to go back to the to my drawing board and do the stability analysis all over. But then after half an hour, these frequencies started to grow. So at first you won't see this, because they're really small, but when they're above the quantization level of your AD converter, they will be there, and they steadily grow. So after about half an hour, this showed up, and it gets worse and worse and worse. And so, yeah, don't let them fool you. At first you think you have convergence, but when you keep the learning on, you might up having a diverging signal. So you have to do something about this. I also did it with a D which was slightly larger than the boundary I found, and I kept this running for more than an hour and nothing changed anymore. So after a few days, who knows what happens, but I ended I ended at a little bit more than an hour of experiments, while the motion was about 1 second. So that gave me some confidence. So. You can never be sure if you keep it running for a year, but okay, your system might actually change due to some thermal properties, so then you might end up having a diverging signal. So what I more or less say is keep on the safe side of this, so take a D that's twice as large as that, so that allows you some robustness in your, allows you some change in properties of your system. I think we will have a short break now. Or no, wait a minute. I only have one sheet left, so on this. So we started a time indexed learning controller to get more insight in the learning behavior of the B-spline network. We needed this to be able to predict what would happen in the multidimensional case. And the time indexed learning feed-forward controller works quite well with only a low number of weights. You only have one dimension, so you don't have a large number of weights. We were able to obtain a quite high performance. We had fast learning, and in our opinion, if you compare it to the other learning feed-forward controller, the disadvantage was that we could only perform one specific motion. So it doesn't necessarily need to be a disadvantage, but to the applications we addressed, it was. And you need some sort of retraining when a motion changes, but training goes quite fast. Within approximately eight motions, you're there. So, but this learning feed-forward controller, as it uses the B-spline network, will not give you a zero tracking error in comparison to the iterative learning controller. But for our applications, it gave a sufficient tracking error, which was what we strived for. Okay, let's have some.
All right, thank you.
though. Until now, I talked about the time-indexed learning feed-forward controller, which was basically a repetitive controller, just with a different storage mechanism. And I more or less did this to get insight in the learning behavior. I didn't do this because I think this is superior over the repetitive controller. I only did this to get more insight in the learning behavior. However, the thing we were interested in was the tracking of arbitrary motions. So that's what we get back to now. And the thing we should keep in mind is that what we learned from the past 1.5 hours is that choosing the width of these B-splines influences the stability of your system. So in which way this will influence the stability in the reference trajectory case will become more or less clear. Still quite an open issue, but it will give us some insight in what might happen if you apply this. So you can. So all of that was just to gain insight. The things we let's see. The things we have to design in the general learning feed-forward controller are again the feedback controller, which is often present. Now we have to also make a choice of the inputs of the B-spline network, which is a multidimensional network. We have to choose the distribution, which influences the stability, and we have to choose some sort of learning rate. There is with a time-indexed learning feed-forward controller, there is a strong connection with iterative learning control. So the stability criterion that I derived said that once the phase of the closed-loop transfer function, the complementary sensitivity function, goes beyond minus 90 degrees phase shift, there's nothing you can do, so you end up having unstable behavior. Actually, you can also get this unstable behavior before that. So the transfer function might go out of the unit circle just before that. But you can always correct for that by lowering the learning rate. So you actually might end up having a low learning rate, and it actually depends on the peak in the complementary sensitivity function. So the higher your peak is, the lower your learning rate, the lower the learning rate you have to choose. So if you do quite well there, you get a relatively high learning rate, and things will go right. So that's more or less what we learned from the past 1.5 hours. This is where I would like to go into this, treat some design issues, and then I would like to show some applications, and afterwards perhaps some optimization, and if there's some time left, some other applications. So what we want to do, the dots over here, you can see in the handout that my sheets came out completely wrong. So I also in correcting them, I also removed the dots over here. So for the random motions, we can't use the time as an input as you do in iterative learning control. Instead, you choose the reference, the R dot and R dot double dot. As a matter of fact, you might choose more. You might include more of these, even go further, including the jerk, etc. But when you keep in mind the class of systems we were considering, which was the rigid body mode of the system on which some nonlinear disturbances act, it's actually not that useful to include more. So in most applications, you will see only up to 3 inputs. So for the repetitive motions, you should include, you should use T. You should simply apply repetitive control, which works quite well. The first design issue I step over the feedback controller design because that is not the scope of this workshop. So there's a whole lot of literature how you can do that, and I won't treat that now. So I will move to the next design choice, which is the inputs of the B-spline network. And at first at our laboratory, we really followed the intuitive approach, saying that, okay, we have this plant, and what kind of disturbances act on the system. If it's a position-dependent disturbance, okay, you have to include the reference position in your feed-forward controller. If it's a velocity-dependent disturbance, include the reference velocity. And in the linear motor case you saw, it has some cogging, which is a position-dependent disturbance. So you end up having a feed-forward controller that has the position as an input, reference position. You can also do this from a more theoretical point of view. And you see I still didn't get all the signs right, so that should be an integrator over there, not a down pointing arrow. Gives you a whole new approach. So you can more or less write a mechatronic system like this, in which the states consist of positions and corresponding velocities, and you can manipulate all the states and end up having some nonlinear disturbances. The brackets are corrected somewhat, but still not perfect. I will see to it that the perfect version gets on the internet. So you can more or less write your system like this, and then if you have some qualitative knowledge about this, you don't actually have to know all the numbers or the exact magnitude of your disturbance and of your dynamics. You simply have to know what sort of dynamics is in there. Then you can write the desired feed-forward signal as a function of these values. So you don't need to have an exact model of your system. You simply have to know, okay, what kind of dynamics do I have, and what kind of disturbances act on them. So you don't need to fill in all the equations. And more or less for each of the terms that's in there, you need one feed-forward signal. So the brackets have gone here as well. Some of them remain, but a simple system is a mass on which some friction works. And you can write down all the equations and end up with a desired feed-forward signal in which we see an acceleration term, which is the mass. We don't really have to know the mass. We just have to know, okay, the mass is unknown. And there's a velocity-dependent term in here. So if you follow the really intuitive approach and say, okay, I don't know mass, that's an acceleration-dependent disturbance, and I don't know the friction, which is a velocity-dependent disturbance, I will include those two in the feed-forward controller.
The superscript D in the equation?
Desired. Might also be subscript or just a matter of notation, which is not very common, I guess. But so we end up having this network. So there's simply a neural network, which should be a B-spline network, that has the acceleration and the velocity-dependent term as an input. So this is actually quite an intuitive approach. And from this you can also see that you can't. So at most these add up to the R double dot, and there's an R over here. If you have a multi-dimensional system, for example a robot manipulator, the R and R dots of several joins might be in there. So for this is a single input, single output system, of which we only have one set of R dot and R dot dot in there. But if you have a multi-input, multi-output system like a robot manipulator, you might end up having a couple of these that have the reference signals of all joins in them. But in that case, you are heavily confronted with the curse of dimensionality. So that I wouldn't advise people to. So keep in mind that this really works for a limited class of systems. But there are quite a lot of systems that are in this class, so it's not completely useless. Then you should select the B-spline distribution. And what you select is both the number and the position of the B-splines. From the previous section, we know that the number of B-splines influences the stability of the system. But it might also influence the learning, the generalizing ability. So you want to choose the right number of B-splines. If you choose too many, you end up having a high accuracy, but or many, but not too many, because you have too many. When you have too many, you end up having unstable behavior. If you choose many, you have a high accuracy, but you have a low generalizing ability. So if you follow a trajectory that's close, you might not end up having a really good improvement. So you want to choose the right number of B-splines. And this is more or less dependent on what sort of disturbance you're trying to correct for. Also, if you use quite a low number of B-splines, the position of the B-splines becomes important. I'll try to show that over here. So the green line is the line we would like to approximate. Think of this as the cogging disturbance in the linear motor, which is a sinusoidal effect. And if you try to approximate this using this B-spline distribution, which gives an output which is linear between these tops, you see that we are actually able to, more or less roughly, approximate the function. However, if we choose this B-spline distribution, in which we would try to approximate this bump by a straight line between these 2 points, we end up having no approximation whatsoever. So if you choose a low number of B-splines, the position of your B-splines becomes more and more important. So this is just if you choose many, you have sorry, you have slow learning. Yeah. Yeah, that's true. Yeah, that's only an extreme example. So if you choose many B-splines, you have a high accuracy, but you need many training samples, and you have a lower generalizing ability. If you use less, you train faster, you have a better generalizing ability, but you end up with you have to make a good choice of where these B-splines are positioned. So you might pick the number of B-splines which is somewhere in the middle. So, and also the number of B-splines, which also was addressed in the previous speech. So if you choose a high number of B-splines, you're able to approximate all these high frequencies. You might not even want to approximate these high frequencies because they excite your system, like in case of the robot, where you have a really high accuracy on all the joints, but you at the tip you end up having a really poor performance. So you excite the system too much. You might want a little less aggressive feed-forward signal there, and you might end up having not such a good performance at all the joints, but actually at the tip you have a much better performance. So that's a trade-off, and there's still a lot of rule of thumb in there. Just try, experiment, see what happens. So if we choose many, we're able to approximate these high frequencies, which might be desirable. If we choose too many, we end up having unstable behavior. If we choose a low number, we're not able to approximate these, but we might approximate just those frequencies that we actually would like. In the previous hour, 1.5 hours, I talked about the width of the B-splines and the relation with the stability of the system. At this moment, it's still an open topic how this works in the multidimensional case. So this is a two-dimensional B-spline distribution. If you run through the B-spline distribution from this side to this side in a straight line, the shape of the B-splines, of the multidimensional B-splines, will look like this. So I will use this grid. If you run through the B-splines in this way, you will see such a B-spline distribution. So you get the triangles, which we did the stability calculations for. So you can actually apply that stability criterion to the B-splines you have over here. If you move them through them in this way, you also end up having these triangles. But if you move through them in another way, you get a completely different shape of B-spline, which is not triangular anymore. So also the speed at which you run through the B-splines is not if it's not constant. You end up having different shapes of B-splines. So you really can't. There's no one-to-one projection of the criterion you have on the time domain, on which it was all very clear, to the reference domain. So, but it does give some insight. So you know, at least you know when you're wrong. So we don't know when we're right, but we know when we're wrong, and we are always a little bit on the conservative side. So if you, one thing to do is to just print, display the shape of the B-splines as a function of the path. If you run through the multi-dimensional B-splines in this way, you can make a projection of each B-spline on the time domain, and you get a little bit of insight how fast you're running through these B-splines. So if you're running through these B-splines at a higher rate than we derived at the in the time domain, you know you're wrong. So you know you're going to end up having unstable behavior. So it's still much an open issue, but that you can give some predictions. And I will show it to you in this slide. So again, I have the two-dimensional B-spline distribution. I have a rough one, and I have a more accurate one. And on this side, I placed on the x-axis there is the reference position, and on the y-axis there is the reference velocity. So if I have this uniform grid, and I run through the B-splines at this lower rate, a low speed, I end up having these triangles, of which I can calculate the time it takes to run through these B-splines. If I run through them at a higher rate, I end up, in the time domain, end up having less wide B-splines. So I actually, from the previous stability analysis, can predict how fast I'm able to run through these B-splines before I get unstable behavior. So, and this directly shows where things go wrong, because if you have this uniform grid, you calculated the highest rate at which you're allowed to run through these B-splines. You want to run through them at a really high rate, so you end up having quite wide, quite a rough distribution on the x-axis. If you, however, that's over here. So, for example, if this is the maximum time of the minimum time you have to stay in a B-spline to be stable, and you run through them at a higher rate, you see that on the time domain, you have these B-splines that are less wide, and you will end up having unstable behavior. So you want to prevent this, and you want to choose the B-spline distribution in such a way that at this high rate, you see the B-splines having this width in the time domain. So what you end up with is a very conservative B-spline distribution. So up here, if you run through these B-splines at a high rate, you see in the time domain, you see this. If this is the minimum time you had to be in the B-spline, as you calculated from the stability analysis, you're fine. You're going to end up with stable behavior. So if you run through these B-splines very fast, you end up having a very conservative B-spline distribution. Because what shows is, when you run through them at a lower rate, you end up having really wide B-splines on the time domain. So you're only able to do a very, very rough approximation. So there's always this trade-off. If you have this if you have this multidimensional case, and you want to both track a really high speed and a really low speed, you're going to end up having a conservative B-spline distribution. And we're going to show how we can prevent this later on. So the conclusions is, when you have this multi-dimensional B-spline networks and you want to track both high speeds and low speeds, you often end up with having a really conservative B-spline width. Furthermore, if you run through these B-splines in a straight way, you can apply the stability analysis we showed in the previous 1.5 hours. However, if you don't, there's not really a theory that supports you. You can more or less hint on whether you will be stable. Furthermore, choosing B-spline distribution might be quite difficult to design. So there's a lot of engineering in there, trying and then going back, and so it's an iterative procedure to get to the right B-spline distribution. We would like, however, what we would like is don't have this conservative B-spline width. We want to have, at a low rate, we want to have a high accuracy, and at a high rate, we want to have this stability. So what do? Instead of the B-spline network in which the feed-forward signal is stored, use this as a filter, as a Q filter. We add an extra Q filter on the learning signal. So in a normal way, if we run through here, we encounter the difficulties with the B-spline distribution. However, if we filter out all these high frequencies which cause the unstable behavior, we're fine. So what we do now? So I will show it to you on the blackboard because it might go a little bit fast. So what I'm more or less saying is if you have this grid, and over here I have the reference position, and over here I have the reference velocity, and at a low velocity I'm stable. So I move through the grid at this pace. Over here I'm stable. If I go through here at a higher rate, these B-splines seem more narrow in the time domain if you project them onto time. So over here, you're going to end up having this unstable behavior. What is this caused by? It's caused by the relation between the signal that's in here and the signal that comes back. So there's no extra filter in there. So what we thought of is, okay, we might filter the signal that comes from this again, filter out all the high frequency parts that cause this unstable behavior, and then feed that signal as an error, as a learning signal to the neural network. So what it does is, if you don't have this, you have this situation, you have the high frequencies coming from here, this network is able to learn these high frequencies, which cause unstable behavior, and you end up having unstable behavior. If you filter it again, this neural network might insert these high frequencies into the system. However, this neural network, the B-spline network, filters them out. You might also take a Q filter. And the filtered version, so the low frequency feedback signal, is then used as a learning signal for the neural network. So you end up having a low frequency learning signal which prevents the unstable behavior.
Why do you use a neural network rather than just a filter?
It's because I did I spent a lot of time on the analysis to calculate the width of the B-spline. So that was the first thing that came into my mind. And I did this at the end of my PhD. So it was just a wild idea. Let's see if it works. I did all this analysis, and I thought, okay, now I have this really nice criterion. I might as well use this. So I used this, and it worked. But you have to keep in mind that you can also use all sorts of other filters, and I also.
I would expect it.
Yeah,
Normal.
that's true. But this is just due to the limited amount of time. And this was the first thing that came into my mind because I did this nice analysis. I used this one. But you can also use other filters, and that's an interesting topic. And you shouldn't restrict it to this. So I'm not saying that this is the perfect solution. It's just a solution that came into my mind when I worked on this.
I'd like to comment on that also. You can do some analysis. It shows that if you use a B-spline as a filter, it actually has good cutoff property. So it's sort of a high order filter, and also has constant phase over low frequencies, more or less. Of course, it's not a linear filter, but it has no extra phase. But of course, you can do zero phase filtering, I guess. But it's sort of an ideal filter in a low frequency.
So we're.
Well, zero phase still has the relatively fast
decay.
cutoff.
So, but I have to say this was only the first thing that came into my mind. We didn't have more time. That's why that's where we stuck to this. But we are looking into other filters as well. So So looking at it in the time domain or on plots, if this is your learning signal, which was generated by PowerPoint, so this is not an actual learning signal. But you can see that there's a low frequency part and there's some high frequencies on there. And if the neural network is able to learn these high frequencies, you will get unstable behavior. So what we would like to do is filter these out. And you can see that if you make a B-spline network approximation of this, you approximate it using the straight lines. You filter out all the high frequency parts. So you also filter out some of the low frequencies, but for our accuracy, that's sufficient. So we didn't need a more accurate motion. So what we call this, the learning signal that is the filtered version of the error signal, is a regularized learning signal. And this signal is actually fed into as a learning signal for the other neural network. And
you didn't run into the high frequency, but those sharp corners, like when you're adding high frequencies back in.
yes, but these do not cause the unstable behavior, because these are caused by the filtering, not by the other network itself. This is a time filter that runs with the that only runs in time. So it's not repetitive. If you have these high frequencies coming from the neural network that also generates the feed-forward signal, then you end up, if you perform motions over and over again, then it's repetitive. But this filter has a different period, so so it's not repetitive. It doesn't blow up.
It doesn't feed back into itself.
No, it doesn't feed back into itself. That's it, yeah. And the other one does. So that's exactly what it is. And I have to say, we only tried this in simulation. In simulation, it worked. So I haven't tried it on a real system yet. So it's more or less it's only an idea, a hint of how you might solve this. So otherwise, you end up having these really conservative B-spline distributions, which are not very attractive. Oh, there's still some. And you can also do that with the learning rate. So there's this. All we did now was have a straightforward choice of inputs. So we just chose a multidimensional neural network, B-spline network over here, and that gave us the curse of dimensionality. However, there are often separate disturbances acting on the system, which not all are a function of all the reference inputs. So if you have three disturbances acting on, or if you want to approximate a function of three, that is a function of three variables, the position, the velocity, and the acceleration, which has this form, which actually consists of three separate parts that do not depend on the same variables. You might approximate it with a multidimensional network, but because it consists of separate disturbances, you can also use three separate networks to approximate this. And this is often what you can do to overcome some of the curse of dimensionality. So you have an additive network structure, and also you can derive this from the equations. So for the moving mass with the friction on it, we first applied this network structure having two inputs, which does not give you that much of a curse of dimensionality, but it requires large training periods. You can also use two additive networks. So one that corrects for the mass, and one that corrects for the velocity. And you have two one-dimensional networks, and that's much more attractive than having one multi-dimensional network. However, there are always problems. You cannot train all these networks at the same time. So because you do not, if you do not apply a path that has persistency of excitation, some networks might learn disturbances that are caused by other things than what they are supposed to learn. So you have to, I will get into this later, so it's hardly possible to get all these networks learn at the same time. So therefore you have to train them one at a time, and you need to design a special learning procedure for this. And the way in which you should choose these training motions is that you try to find a motion that makes one of these disturbances dominant over the other ones, which is not always possible sometimes. And then that physical effect becomes dominant. You can train that. Then you hope you got rid of that effect. And then you train the next one. And this is not a very straightforward procedure. So it requires some experience. So it's not like you turn it on and it works all by himself. Whoops. Ah, there it is. Okay, so I would like to conclude with the design of the learning feed-forward controller. So first you have to design or have a feedback controller. Then you choose the inputs of the B-spline networks on the basis of process knowledge. You select a B-spline network structure, either one large B-spline network or a structure of additive networks. Then you design the B-spline distribution, keeping in mind the stability criterion. And if you have an additive B-spline network structure, you have to perform some sort of strategic training procedure in which you train one of these networks at a time. I will get into the applications now. And this is the one Kevin referred to in his laboratory. This is our mobile robot. We applied learning control to this, but first I would like to comment a little bit of what they were trying to do with this. This one was designed for flexible factory automation. And it was actually used to assemble mixers. So, and the idea was that nowadays these factories are quite inflexible. So you make one product, you have a production line. You want to make another product, you have to reassemble your production line. You have to change a lot. And that costs a lot of money and time. And they wanted to save this. And they also tried to save some space. And because they wanted to save some space, they came up with this huge mobile robot, which consists of a lot of batteries here in the lower part. There's quite a complicated computer structure in here, so the embedded software guys really had a challenge here. And on top of this structure, there's this robot. And the idea was that this robot goes to some sort of docking station. There's it docks onto the station. It gets all the parts it requires. And it undocks, and while it drives to the next docking station, it assembles these products. However, the robot was quite large, so you need a really huge factory to have many of these running. So it was more of a test case. This one didn't go into production. The position of this robot was determined by means of a laser sensor. You had the beacons all through the factory. And there's this rotating laser sensor on here, which determines the position. And in my opinion, this was not a very useful application. I think your military applications are much more useful. So for the factory automation, it didn't turn out to be the thing they wanted. But to be able to dock into a station, you need quite some accuracy to be there, because there's this fixed docking mechanism, and it has some nice features, and there's a lot of flexibility in there, using these three blades, which the docking station docks onto. So at the side of the robot, there were these three blades. So this is the side of the robot, and like this one sticks out. This one sticks out. I don't draw it in the right way, but these are. And each one of these is very flexible. So if you bump into something, this will just it's very flexible. Nothing happens. But if you grab them all three at a time, they're put under an angle, so 120 degrees. And if you grab on them all three at a time, you have a very stiff connection. So, however, even though it was flexible, they still needed quite some accuracy to be able to dock correctly and also not to bump into each other. So that was more or less a challenge, to make this mobile robot track a trajectory quite accurate. There were some extra challenges over there because the mobile robot couldn't go anyway. So the robots that the mobile robots Kevin has have these nice properties that he can rotate the wheels in any direction. You can virtually go everywhere, anywhere you like. But we can't. So these two wheels are fixed, and this one is able to rotate. So if your trajectory is somewhere around here, you can't simply go there in this way. So you have to calculate a trajectory in which you want to get there. So all that was incorporated into the feedback controller. So, and you don't want to get there too fast. So that's quite a research topic, how to get back on trajectory once you're off. And the main disturbance that acted on this system was unknown friction. Because it was quite heavy, and the wheels had some friction which was quite unpredictable, but constant. So we designed a learning feed-forward controller for this. We had a normal feedback controller that acted on the system, and it had the displacement in the x and y and rotation direction. It also had the error of the velocity, and then it calculated how to get back onto trajectory. And this is more or less what came out after the learning procedure. So we tried to follow this more or less 8 over here, and without oh, it's still in Dutch. So without the learning feed-forward controller, you get the wide error, which is about 120 millimeters, so 12 centimeters, which is quite far off. It's too far off to be able to dock correctly. So we were not able to dock correctly with using this mechanism. So we thought we might as well apply learning feed-forward control, drive this 8 a lot more. And after a couple of trials, we were able to really decrease the tracking error. So in this application, we were not that much interested in performing random motions or arbitrary motions. We were more or less interested in driving a small number of motions, because these machines go from one place to the other, and there are not that many ways to get there. So you won't let the robot spin around, go off that direction and then come back. So they more or less follow this fixed trajectory. So we trained it using a couple of these trajectories, and those were able to get us moving through the factory.
So if you go from one trajectory to another one, you have a different set of weights then that you...
No. That's all the trajectories are in the learning feed-forward controller. He has to learn it. Yeah, he learned them all. Yeah, and it's a path generator that decides which trajectory to use. So I don't know if this is of any relation to your. I don't know how you determine your position. You don't have any beacons, do you?
No, we use some odometer GPS. We have high precision GPS for outboard, or just wheel counting. And we never slip, so wheel counting is fine. But a question would be, how you learn, say, several trajectories, your network is converged. Now, what if you want to do this 8, but with double the size?
You would have to train that again.
We'll say constraint. So
Yep, it would.
because there was some interesting work done by XU, Professor Chu in Singapore. He called it direct learning, and he looked at 2 types of things. He said one where the pattern is the same,
Yeah.
but the time we want to make faster or slower. And he wanted to say, if I learned this one with a certain velocity profile, but now I want to change the velocity profile with the same spatial one, can I do something from what I learned before? And he did that in an ILC setting. He also said, suppose I have this diagram,
Yeah.
and I've learned at this reference path, and now I want one double size. Can I extrapolate from what I learned in the first one? And he had some success with
I think it pretty much depends on what you're compensating. So if you compensate for the if the stuff you're trying to compensate differs once you scale it up, so then you would have to learn it again. So in this case it is the more or less the friction. So if you scale this up, the orientation of the robot will be a little bit different, and we had to train this all over again. So this doesn't give you the solution he obtained using the direct learning. But we were able to get a nice performance of this.
As you add some new reference trajectories,
That-
you get a good error with fewer trials of learning?
Yes, if you what a behavior of the neural network, of the B-spline network is if you follow a trajectory that's quite close to this one, you get a good performance. However, if you train that one, it's more or less of an average between that trajectory and this one. So you give up a little bit of one, so you increase the error a little bit, and the other one gets a little bit more accurate. So in the end, there's this optimum where the error is distributed over all reference trajectories.
I'm just thinking the application for our robots, the command line grammar we use, we decompose all paths into a summation of a finite number. But what may be different, I mean, an arc is an arc, and a line is a line. The only thing that's different is kind of how you concatenate them.
Yeah.
And the length of the line or the radius of the arc. So there was a nice way to learn a unit arc
Yeah.
or a unit line, and then extrapolate to variables in terms of the radius or the length.
But
Concatenation, but
don't the errors you encounter heavily depend on the surface you're riding?
sure.
Yeah. Okay, but because those you couldn't incorporate those. But so you're planning on these toy train tracks, more or less making a trajectory out of those?
Right.
Yeah. Okay.
But we didn't do any learning at all.
You would need an error in the position, so you would need an accurate positioning sensing device. In which, because we were in a factory, we were able to use beacons, and that's in a factory. That's no problem. Or you can simply paint the floor in black and white squares. You can think of all sorts of stuff. But out in the field you can't. So you need some measure of where you should be and where you are. So I think to you that's more of a problem.
But you do have a velocity profile.
Yes. Yeah.
So it's not only the geometric.
No. There's also a velocity profile. Yes.
And there's some underlying assumption in everything you're doing, and I'm guessing, I guess I should ask, and that is that these paths are realizable.
Yes. Yeah.
So a solution exists.
Yeah.
I mean, this is something that hasn't come up in this meeting, but very much in a lot of the ILC literature, there's always assume some X desired that will produce,
Yeah.
they assume there's an input that will produce the desired output, and then you show you converge to that. But other literature, they don't do that. They try to get as close as possible, but I guess here, there's a velocity profile and you was taken into account.
Yeah. Yeah.
Acceleration limits.
You always apply trajectories that are realizable. Yes. You have to keep that in mind. Otherwise, you go into saturation of your actuators, and there's no use doing that. So.
That's why the quadratic code stuff is good, because it allows you to minimize what you ask for and what you can achieve.
But
Did use that kind of approach at 7%, that you have an index along the
you can. Yes, you can. That's true.
So you
You can. Yeah. Yeah. That's a different approach. We didn't try that one. And unfortunately, this robot doesn't exist. I don't think it exists anymore. So no, it's because the project was closed and it was too large. So and office space cost money in the Netherlands as well. So they got rid of it.
But to me,
Unfortunately.
you can do this kind of whole path with one V4 controller without an index every time there's a parallel line. This is stronger.
Yeah, yeah. In our case, the robot simply stops, so there's no intelligent path planner that moves around the robot. So it's all based on the fact that it has to operate in a factory, and that there's some sort of supervisor that supervises all of these. If you have multiple of these, that supervises all these mobile robots. But unfortunately, for the factory, it wasn't. This solution was too large, so you need smaller equipment. An application that I referred to earlier is a linear motor, and we got this linear motor, and the purpose of the linear motor was to increase the accuracy of the linear motor, because it's a rather low cost at that time, a low cost linear motor, and they would like to do some scanning operations with it, and for medical purposes, for example. And they encountered a number of disturbances that prevented this. And the large one was cogging. So if you move this translator back and forth, you will feel a huge torque ripple. So it's because of the iron in the translator and the magnets in the base plate. And this you can see this strongly in the error signal. Then there was a lot of friction in there. So at our laboratory, we didn't know what maintenance this thing needed, so we didn't put any oil or anything in it for 2 years. And actually, we got a maintenance manual, and it said apply oil every month. So after these 2 years, we had a setup which had quite a lot of friction, and was very suited for the learning feed-forward control, seeing if it still works if you don't stick to the maintenance manual. And we put some unknown mass on here, and there are also errors in the computation, but I won't go into those. So those were basically the errors we tried to correct. And yes, so we in the first controller that was present, there was an integrating action in there, to get rid of all the friction effects. And as Yang Wang referred to earlier, if you incorporate that integrating action in here, and you feed it into the neural network, you will actually have 2 integrators behind each other. The one not being a real integrator, because it's a B-spline network, which is not a non-linear integrator. The next time you get back into the B-spline, you encounter the integrating action, but that's not something you would like. So, and because we already had this feed-forward controller, or we are going to make this feed-forward controller to compensate for the friction, we lost the integrating action in the feedback controller, which of course reduces the tracking error without a feed-forward controller heavily, or gives a much higher tracking error. Then we had added a neural network, and there was an unknown mass. We do have some friction, of which we first thought that it might be only velocity dependent. And there's a cogging, of which we thought that which can be quite accurately modeled using only the position of the translator. So this is pretty much what we ended up with. I've not given the actual accuracy after training for the learning feed-forward controller, but it's if you use the multi-dimensional network, the error typically goes down from 100 microns to about 10. So 10 to 5. So you get a huge improvement. And this already happens after, like say, 8 repetitions. So you're able to improve the performance, which we downgraded first because we took out the integrating action, of course. But you're able to improve on this downgraded performance in quite a fast way. Then we, as we worked with this robot, with this motor more and more, we understood it better. And we got more insight into the nature of all the disturbances. And one of the funny things, we still don't understand why this is, but we saw that there should be a dot up here. We saw that the cogging, so the position-dependent disturbance, from going into the one direction was actually different from cogging going into the other direction. And not only in amplitude, but also in the frequency. So, and we still don't know quite what was going on there. So what you see is that if you go in the one direction, you have this really nice, well, really, it's not really nice, but it's a more or less a sinusoidal effect. But if you go in the other direction, it's also sinusoidal, but then suddenly you have something like this, and then it's sinusoidal again. And we still don't actually know what this is. So we're puzzled. The people who made this are also puzzled. But it was in there. And we tried to compensate for this using the learning feed-forward controller. And the experiments we previously did with a multidimensional network showed that we were able to compensate for this. So the effect does not occur when you stop learning. So actually the learning feed-forward controller was able to learn this. So it's a disturbance that happens each time you travel a trajectory. So it's repetitive. So we don't know what it is, but we know it's repetitive, and we know it depends on position. And that's actually all we need to know. It would be nice to know what it is, but
the two curves you just draw, what is the x-axis?
this is the position.
Position, not the time.
No, this is the position. So you go from one side to the other, and you expect a sinusoidal disturbance. You encounter it in one direction, you go back, and then there's suddenly this high frequency component in here. Perhaps Dick, he worked a lot with linear motors. Perhaps he knows, but no, it's another one. It might also be the poor maintenance. So. Yeah. So, but we it does, but it's strange that the frequency changes suddenly. We can just discuss about it, but the commutation errors I won't go into those. And then there was some nonlinear friction, and that also had a different sign going in the one direction and in the other direction. And then of course there was the unknown mass. So we ended up having quite a lot of B-spline networks. So this one is for the commutation, but we will skip this one. Then there's this one B-spline that tries to compensate for the unknown mass. Then there are two B-spline networks that try to for the velocity-dependent disturbances, which we assume to be friction. And then there's these two networks that try to learn the cogging. And as I said earlier, let's see what slide comes next. Because going back and forth gives different results. So we had one B-spline network for going in the one direction, and one B-spline network for going in the other direction, and that actually solves the problem. Yeah. So, however, we got a whole lot of B-spline networks now, and if we turn these on all at the same time, what we saw is that these position-dependent B-spline networks take over, try to reduce all the error. So the first time you perform a motion, so you go in the one direction, this position-dependent B-spline network is able to learn the entire error. So it will also compensate for velocity-dependent disturbances, because you go back, you go forth, you encounter unknown mass, you encounter friction, and you encounter the cogging. And if you only turn, if you move in one direction, this network will learn them all. Even if you don't want them in this network, it will grab them all. And what you do afterwards, it doesn't matter. You can't get it out of here into the other networks. That was one of the problems we had. We tried to train them all at the same time using all different sorts of trajectories, but what we ended up with was one network learning everything, or learning disturbances of the other network, and we were unable to get them from one network into the other network. So perhaps if we did a really large studies to the trajectories we were going to apply, this might be possible, but it's a problem. So, and you don't actually have this problem in the three-dimensional case. So if you have one network learning it all, it's okay. So it learns it exactly in the right spot.
But in this problem, why you have to specialize that? Can you just do one single network?
In which?
In this problem, in the linear model problem?
Yes, you can have one network that has R dot and R dot dot in there, and it will take care of everything.
Yeah.
So no problem there. You automatically, because they're because R dot can be positive and negative, you automatically compensate for that. It can store both in there. It can store everything. So it just needs more learning trajectories. Because cogging, if you drive back and forth a couple of times, you learn the whole cogging. However, if you use the multidimensional network and you learn cogging for one trajectory and you're going to perform a completely different motion, you will have to learn the cogging all over again, even though you learned it in the other trajectory, just because it's somewhere out there in the other dimension. So if you look at it in the two-dimensional space, so if you learn this trajectory, it will be able to more or less learn reproduce trajectories which are close. So, and if you learn this trajectory, you learn cogging, you learn friction, you learn the unknown mass. But if you're going to perform this motion, you have to learn all over again. Even if you learned all the trajectories over here, there was nothing in the table over here. So you have to learn all the effects all over again. And we thought that's a pity. Might as well try this. But the problem with this is that you can't turn them all on at the same time. So it involves some engineering.
Did you succeed in creating something that works?
Yeah. That's what I'm going to show now. So what we first did is we don't want to encounter the velocity and the acceleration terms. So we make these things move back and forth in a really slow way. So you go one direction, and all you're going to encounter is the cogging and the Coulomb friction. And it's the Coulomb friction can also be stored as a on the position domain. It doesn't matter. So, and what you see is when you go back and when you go forth, you have and you do that a couple of times. These are actually the mappings that are in the B-spline network. So these mappings are going to compensate for the cogging and the friction, or in the Coulomb friction. And this one is going to do it in the negative direction, and this one is going to do it in the positive direction. And you can see that they're actually over here. This nice sinusoidal, and over here there are some maintenance problems. So you see the errors in the you can see the cogging errors. But if you actually take the compensation in the positive direction, you can see that over here there's something different is going on. So it's not. There are no nice sinusoidal functions over here. It's more or less, who knows what. So, but these, after performing these motions at extremely low speed, we were able to compensate for these. So what we did was we applied a really slow acceleration and a really slow velocity, such that these effects are not dominant. They're in there somewhere, but they're very, very small, so they don't affect the outcome. So we now more or less learn the cogging, and in theory we would be able to perform arbitrary motions now without a cogging effect in it.
Any comment as to why the DC level is different on the two?
That is the Coulomb friction. The Coulomb friction is also in here. If you go in one direction, you will always encounter the Coulomb friction. If you go into the other direction, you're also always going to encounter the. So, but if you have this, and if you select a position-dependent, if you select this position network, but it depends on the direction, the Coulomb friction will be in there, and that's no problem. You're always going to encounter that, so you will have to take care of it. If you would have only one mapping, if the cogging would be the same going back and forth, this level would be the Coulomb friction. You hope it cancels out. It might not, so then you need two. But if it cancels out, you will see this exactly around 0. If it doesn't cancel out, you take the 2. And then we turn on the velocity and acceleration B-spline networks, And here are actually the velocity-dependent networks, and the reason why we have two is because of the stiction effects around zero. So this is still an open issue, how to deal with these stiction effects. They're quite difficult to deal with. We were able to decrease them only a little bit, but the phase shift between where your actuator signal and what you get back easily gets larger than 90 degrees, because you apply a signal, your mechanism is stuck, and it suddenly comes loose, and then you're going to encounter what you did. But on a very small time domain, which you need to encounter to compensate for stiction, there's no effect, so your manipulator is stuck. And the acceleration network is came up with this approximation. So we applied all these, and it turns out that the accuracy, there should be some pictures in the thesis. The accuracy you're going to achieve with this is actually not as high as the accuracy you're going to achieve in the three-dimensional network. So there are still some effects that are coupled. So or the training procedure was still not performed good enough. So, but the error went down from 100 microns, so I guess 20 microns, but you have to look that up in the thesis. But it was approximately a factor 2 worse than the one network. But it was still quite acceptable, because after only a small amount of training motions, you were able to perform a large amount of motions with a high accuracy. So and for our application, that was enough. So if you really need this really accurate motions, you should apply the three-dimensional network. But if you don't need that extremely high performance, and you want easy training, then this one, you should apply this one. Yes?
Is the three-dimensional more sensitive to noise? In other words, if you have with super motion, does it pick up the characteristics of the motion, and is this more independent of that?
The noise is more or less cancelled out by the filtering of the B-spline networks. So they have these filtering properties which cancel out noise. But this is actually because you force one function, you force it to learn one function. So if the other one is able to learn all different sorts of disturbances. So if you have a random disturbance, then the other one is going to learn it. But in this one you really force a limited class of disturbances to be learned. So this one is actually less sensitive to those. Yep. So the multidimensional B-spline accelerator had what I call the poor learning behavior. It takes a lot longer, and you have a less generalizing ability. However, you're going to end up with a higher accuracy. And if you use what we call parsimonious network structure, the additive networks I just showed, you have you need a special training phase, but you have lower requirements, and you have a really good generalizing ability, because you can perform arbitrary motions with that. However, the performance was less than the other one, so that has to be said.
You, in some nice way, use the separated neural networks as an initial training for the.
Yep. You can, yeah. There are all different sorts of things you can do afterwards. If you want to take, for example, perform 5 motions, repeatedly perform 5 motions and then 5 other motions, you could start with this as an initial set, and then add a ILC controller to it. So all different sorts of things are can be done. It won't give you the performance of an ILC controller. So it's no comparison to that. So the ILC controller strives for an almost zero error, and this controller won't give you this. So because of the additive network structures, and because of the B-spline network. So, but it has some connections, and it is for different applications. But you really have to distinguish between the both. Then the other application I would like to show you is what we call a electronic loading C. Electronic loading, it should be an S system. Okay, an electronic loading C. And it's actually a flight simulator stick We did this for a company that builds flight simulating equipment. They built both the steward platforms, and they built the controls of the pilot. And these controls simulate the behavior of an aircraft. And they also do trains, and for Mercedes-Benz they did a drive-by-wire, so where they reflect the forces on the tires in the joystick you're having. So that works pretty well. The only problem is though that in the mechanism that's behind the simulating device, there are some mechanical properties that you do not want to feel, because these are not the mechanical properties of the thing you're trying to simulate. So, and as soon as these properties arise, for example friction, in a situation where you wouldn't expect friction, then the whole thing about the simulation is gone. So if the one thing that they have problems with, is that in a steward platform, if you go up and down, you will encounter a so-called reversal bump. It's because of these people used electromotors to drive the legs of the steward platform, which is... Oh, you've seen it in a small version by Richard Longman. So it's more or less all... it's not a very good picture though, but you've seen it with the 6 legs. And if you go up and down and you use these electromotors, and there's these ball bearings in there, and they have friction. And if you go up and down, the controller, which is often a PID controller, has to compensate for the friction in there. And that takes just a little time. But the pilot might experience this sticking effect. And so and then the whole illusion is completely gone. So they tried a learning feed-forward controller to compensate for the Coulomb friction in the legs, and they were quite successful in this. So what I do is, before these steward platforms are used, they do a 15-minute run just to make the whole stuff a little bit warm and make it operable. And after these 15 minutes, they do a couple of training runs. They go up and down, up and down, up and down, and then they learn to compensate for the friction. And during the day, they use that compensation. And then the sticking effect becomes below the perception level of the pilot. So that there's your illusion again.
They're using what technique to get
a dressed-down version of the learning feed-forward controller. And the same arises in this setup. So we built the seat on here and the metal case, so that is normally not in there. But underneath is this. There's a stick. This is the frame, and there's a motor, the ball screw spindle, and a force sensor on here. And what it do is, when you pull the stick, the force sensor forces feels what you want to do, feeds it to a mechanism, and then it drives the motor. And the same that happens in the steward platform also happens here. If you go up and down, in this case back and forth, you do encounter this sticking effect, and that might destroy your illusion. And also there are some the cogging of the motor can also be felt in the stick, but you have to be really sensitive to feel that though. So in this setup, they also wanted to get rid of the sticking effect, because this is a low-cost version. They also have a high-cost version where the stick is not driven through a ball screw spindle, but through a cable. And that's actually 3 times the price of this. And what they wanted to do is make this one feel like the other one and sell it at a medium price. So they actually wanted to get rid of all the negative mechanical properties in this thing. And what it does is, you have the stick, the encoder measures the position of the stick, the force sensor feels the force the pilot exerts on the stick. You feed it in a model, and out of this model comes a reference velocity for a PI controller loop, and this one is fixed in hardware, so we couldn't do anything. We were able to insert some signals over here. So in this model there might be anything. So we tried some models of our own, And you kind of mass spring models, and it feels really funny. And they sell these chips on which there's an aircraft model on there. So what the inertia of the system is actually quite small because of the high transfer ratios in there. So that's not an issue. The main issues were the friction, which was velocity dependent, and the cogging, which was position dependent. And we tried this learning feed forward controller, and it turned out that this. Oh, we tried that one. It didn't work out. It was able to compensate for the friction. It wasn't able to compensate for the cogging. And what happened was that the cogging was because of the poor feedback controller, the cogging was not a reproducible effect. So if this is the period of the cogging on the position domain, the positional error of the device could span several of these periods of the cogging. So you can't do anything in feed forward. You have to be quite accurate where you have to be in the neighborhood of where you want to be able to apply feed forward control. So over here the error was way too large to compensate for this. So what we did was actually apply what I told you shouldn't apply, namely learning feedback control. But we just wanted to see whether it happens, whether it works. And what we saw, what we came up with was this structure consisting of a neural network that has the velocity in feed forward and a neural network that has the position in feedback. And we tried to train them in the same way. And actually, without any theoretical proof whatsoever, we were able to. Oh, this is the without learning control. This is the velocity error you encounter. So these are the cogging effect. Might also be the bearings, the balls in the ball screw spindle, though. That's not actually sure. So this is without learning control, and I think the red one is with learning control. So in the frequency domain, it shows like this. This is, you see a distinct peak in the frequency response, and after learning, we shifted the peak, but this one is below the perception level of the pilot. So these are probably the width of the B-spline. So the sharp edges you get by using a first order or a second order approximation, first order. But we got rid of the really large peak over here. So without any theoretical proof or any insight of how the learning behavior was going to be, we were able to do this. But you shouldn't apply this, but we tried, we succeeded. But you should really have theoretical proof before you do something like that. So, but the funny thing was that at first we had a really poor, or we tried a really poor feedback controller. So you could hardly move the stick. And as you learn, the stick, we tried to simulate a single mass that was floating in the air. So on a single mass there's no friction. So you should be able to just pull it back and forth without any friction experience. So at first we had a really poor feedback controller. And you were hardly able to move the stick back and forth. And it was really difficult to do. And then as you kept on doing this, it became smoother and smoother until at the end you actually experienced the model you were trying to simulate. So please visit Twente and come and experience this. Don't know if you have, but still have a little bit of time left. One of the topics I addressed was the distribution of the B-splines, which was dependent, which determines how good you're going to learn. And we had some time left. We wanted to see if we could generate these B-spline distributions in an automated way. So we used a clustering algorithm to determine the B-spline distribution. So often, in many cases, you are able to, because of your knowledge of the system, in some cases you design it yourself, so you know what you're going to expect, and you are able to design a very nice B-spline distribution. But we tried if it was able to do it in an automated way, and the B-spline network is actually quite related with fuzzy logic. So it's actually fuzzy logic that has a controller that has certain properties. So it's all highly connected. So we went into the fuzzy logic literature and found some ways to determine these fuzzy sets on the basis of data, and that was called fuzzy clustering. And what fuzzy clustering does is it tries to make a model of this data using a B-spline or using a fuzzy set. I don't. Yeah, you treated fuzzy sets. So on top of this, it tries to project fuzzy sets. So these fuzzy sets can be viewed as B-spline networks. These are just ellipsoidal fuzzy sets, but this data is actually clustered using a fuzzy set. And these fuzzy sets, which are in this direction, can then be projected in this way and in that way. And what you actually see is, using this, you can make an approximation if you use a certain type of fuzzy controller. I'm merely saying this to show you that it is possible to do. Don't say that you should do. But these fuzzy sets can be projected, and you can make a fuzzy model out of this and then get the fuzzy sets. Oh, there's still some funny thing. Yeah, it definitely is. So using the fuzzy logic algorithm, it tries to capture this using fuzzy sets. You project the fuzzy sets onto one of the axes, and you can get a linear approximation with some interpolation over here of this. It's more or less the same as we do using the B-spline networks. If we would try to approximate this and we put the B-splines over here, you get straight line approximation here, here, and here. And you can see that actually in the B-splines, the top of the B-spline is here at the beginning of a line, and over there the top of a fuzzy set is in the middle of the line. So it shows you that once you have these intersections, you can approximate the fuzzy sets. It all goes a little bit quick, but it's in the thesis if you're interested. And you can use an iterative procedure in order to obtain a feed-forward signal. So you do one run, you cluster the error signal, derive fuzzy sets of that, and you see what happens, and you keep on clustering, and in the end you will get some sort of distribution. Again, we apply this on the linear motor, and before learning... Oh, it's gone again? Okay. Yeah, just have to walk over here and it works. So before learning we got this error, 3 times 10 to minus 4th. Without clustering we got this tracking error of approximately 3 times 10 to the minus 5th. So that's already an improvement of factor 10. And then we thought, okay, these fuzzy sets might not, or these B-spline networks might not be in the B-splines might not be in the right position. So we tried some clustering, and you can see that actually by using the same amount of B-splines, but just distributing them in a different way, you can get a lower error. This is just to show that it is possible. It's an involved, rather involved procedure, and I don't think you should really do it, but we just try to, if it also to make some links with a fuzzy logic community, because we had a fuzzy logic community at campus, and to be able to communicate with those, it's good to do research on the borders of all of these topics. So, and more of this research can be found on this webpage. Luckily, this sheet came out right in the. And you can find, for people, I only brought a limited amount of theses. The thesis is over there, and there are also some articles on this. So what I would like to conclude with is, we designed a learning feed-forward controller. It is slightly related to the iterative learning control. It should be applied in a different situation. It won't get you the small tracking error as a repetitive controller, iterative learning control gets you when you design them right, of course. But it gives you some other opportunities. And there's a link between learning feed-forward control and iterative learning control somewhere. We already know a little bit about it, but it's still an open topic, which is quite interesting. And it does work in certain applications. So we applied it on the linear motor. We applied it on the Steward platform and on the control loading system. And it allows you to quite drastically decrease the error compared to a PID controller, as iterative learning control and repetitive does, just not as far. Okay, thank you.
Well, thank you. So, in the afternoon we have 4 talks, and we will have 3 different experimental demonstrations you can go to see, and we'll give you the direction and information about those